Hello everyone, I'm Alptekin Küpçü from Koç University, and this is joint work with Muhammed, Babis, and Dave. So our setting is the outsourced storage setting, where for the sake of confidentiality we encrypt our data, but then how do we provide search functionality? So this trivial protocol can provide search functionality. The client encrypts his files, outsources them to the cloud, and then to search, he downloads all his files again, decrypts them, and performs a local search. This will be trivially and obviously secure, but unfortunately extremely inefficient. So what we want is a balance between security and efficiency, and we are interested in index-based searchable encryption solutions. In this setting, we have our files and a dictionary of keywords, and for each keyword, we have a set of files, actually file identifiers, file names if you wish to think, that contain this keyword. Now what we are going to do is we will generate a key associated with this keyword, and this is usually done through a pseudorandom function, and we will encrypt this list with this key. Then we will store this list at, let's say, random locations in our index and outsource this encrypted index together with the encrypted files to the server. So here the client will generate three things: the encrypted files, the encrypted index, and some metadata. The client will keep the metadata locally and outsource the encrypted index together with the encrypted files to the server. To perform a search, the client will generate a token associated with the keyword, send this token to the server. Now this token will enable the server to perform a search over the encrypted index, but only learn the files associated with this keyword. When the server learns those, sends the encrypted files, so now the client can decrypt them. Now what you can observe here is that there is a leakage. We are leaking information to the server. What are we leaking? We are leaking what's called the access pattern, essentially the list of files that are associated, that contain this keyword. Unfortunately, we need to leak this if we want the scheme to be efficient, because we want the server to send us only the related files so that our download is efficient. But notice that here, it doesn't mean that the server knows the keyword or the files. It is done in a way hiding the actual keyword and the contents of the files. They are encrypted, but it only learns the association between them. There is also another leakage called the search pattern, essentially the number of times a keyword is searched for. And this again leaks in many searchable encryption schemes because these tokens the client generates are deterministic. For dynamic schemes, as in our case, we want to be able to add or remove files, there is further leakage. And without forward privacy, what leaks during a file insertion is that the file identifier and file size, of course, the number of keywords in the file, and whether or not these keywords were previously searched for. And why does this happen? With a search, the client is sending this token, which is essentially the key associated with this keyword. And then now we are adding a new file, let's say that contains a keyword that was previously searched for. This token enables the server to link this new file with the old searched keyword. And of course, in the worst case, if all the keywords were previously searched for, then the server knows all these associations. Such leakages in searchable encryption schemes may lead to many attacks: access pattern attacks, search pattern attacks, file injection attacks, etc. And as we said, without forward privacy, each new file can be linked by the server to previous searches for free, essentially. But the good news is that forward privacy prevents this kind of leakage. And this helps prevent some of these mentioned attacks. So with forward privacy, when we insert a file, we leak the file identifier, the file size, and the number of keywords in the file, but we no longer leak any association with this new file and any previously searched keyword. So our scheme achieves forward privacy roughly as follows. So as usual, the client generates a token revealing this associated key with a keyword to the server. The server, as usual, performs its search over the encrypted index, finds the associated files, and returns to the client. Now, in addition, the server also deletes these entries that were accessed. And then the client reinserts these entries with a fresh new key at new random locations in the encrypted index. So on the slides, I will only mention an honest but curious setting, and we will use some non-constant but small client storage. In the paper, we have a dynamic, efficient, parallelizable forward private scheme whose security is proven via simulation. So I will demonstrate our scheme using an example. Let's say we have 3 files. File 1 has 3 keywords. File 2 and 3 contain 2 keywords each. So as you can observe, our dictionary is of size 4 unique keywords. And I will use this notation WIFJ to denote that file J contains keyword I. So let's say file 1 contains keyword 4. I will denote it with W4, comma, F1. We will employ 2 indices. One at the client side keeps for each keyword the number of files associated with that keyword and the number of searches we have performed over that keyword. So these are 2 simple integer counters, nothing cryptographic here. And at the server side, we have a dictionary, let's say a hash map. Now, initially the client can build this index locally and then finally outsource it to the server. So the client will take each file, and for each keyword in the file, it will start with incrementing the counter, and then it will generate the key associated with this keyword. Then it will create a pseudorandom address to store this association of W1 and F1, keyword 1 and file 1, and encrypt this entry with, again, a key derived for this particular entry. So I will show you the unencrypted version of this index, but everything in this index is encrypted. Okay? So the client will switch to the next keyword in the file, increment its counter, create the key associated with this keyword, find the pseudorandom address to store the association of W3 and F1, encrypt it, and store at the index. And the client continues, encrypts and stores W4 F1 association at some other pseudorandom location, and continues with other files, and finishes completing this encrypted index. Now, together with the encrypted files, the client can outsource this encrypted index, and now we are ready to perform a search. So to search for, let's say, keyword 4, the client will generate the key associated with keyword 4, and simply copy this counter and then send these values to the server. Now the server, for each file associated with this keyword, so the counter was 2, so the server will do this twice, it will find the locations and decryption keys for the entries in its index. So it will compute the address, find this location, compute the decryption key, decrypt the entry, and learn that this keyword is associated with file 1. Then it will go to the next entry, find its location and decrypt, and learn it's also associated with file 3. So the query result is file 1 and file 3. The server will just send these values to the client for the client to decrypt. Then the server removes these entries that were used. Okay, simply removes them. Now the client increments its own local counter for the number of searches performed for keyword 4, and then this enables him to derive a fresh new key. With this fresh key, the client will compute new pseudorandom addresses and new encryption keys to encrypt these 2 associations and store them back at the server's index at new random locations. Now to insert a file, let's say which contains two keywords, 3 and 4, the client will again create the keys associated with these keywords, prepare these associations of keyword 3 and file 4, keyword 4 and file 4, encrypt them with these new pseudorandom keys, find their pseudorandom addresses, and then send these to the server for the server to store them. Observe that at any point in time, the server's index only has entries that were encrypted with a key that was never revealed to the server. So for example, keyword 3, we never searched for it, so the server never received a token for it. Keyword 4, we searched for it, the server has a token for keyword 4. But this entry, remember we generated a fresh key for keyword 4, so now this entry is encrypted with a fresh key that was never revealed to the server. Finally, the client simply increments its counters and we are done with insertion. To perform deletion, we need to add another index. So at the server side, we will have this right-hand side index as additional. This index will simply keep, again, this index will be encrypted. It will simply keep, for each file, the addresses on our left-hand side index for entries that are related to this file. That's it. And at the client side, we will keep another set of counters. So for each file, how many keywords are associated with this file. To delete a file, let's say file 3, the client generates the key associated with this file for this right-hand side index of the server, and then simply copies the counter and sends these values to the server. Now the server computes these addresses on the right-hand side index, decrypts them, learns the addresses on the left-hand side index, and now simply deletes these entries, and of course the file. The client also simply deletes its entry, the counter in its index. So at the client side, we have this left-hand side counters for search and insertion operations, and right-hand side counters for insertion and deletion operations. So until our work, there were only two schemes providing forward privacy. One was using an oblivious RAM type of structure, so it was having some polylogarithmic overhead, and the other was using public key operations. So here we have forward privacy together with parallelism and achieving essentially optimal asymptotic complexity with only simple symmetric primitives. We also measured the concrete performance of our scheme with a data set containing roughly 4 million files, roughly 10 million keywords, and 500 million total index size. So 500 million keyword file associations. We implemented this and tested on an Amazon server with multiple cores, but our main tests were using only a single core and compared against the previous work, Sophos. So I will only show one graph for the sake of time here. We have further graphs in the paper. This is the search performance, and this is per entry, per keyword file association. Our scheme with a single core, the red line, takes roughly 10 microseconds per association, and the blue line is our scheme with 5 cores running in parallel, which takes only roughly 3 microseconds. So more than 3 times speed up with 5 cores. So in conclusion, what we see is that forward privacy is a very important feature for searchable encryption schemes trying to resist some of these attacks. And our scheme achieves forward privacy. It is parallelizable. It is efficient. So we only employ pseudorandom functions, hash functions, and at the server side, a simple hash map data structure. And we have a security proof via simulation. As future work, there are 2 main issues. One is backward privacy. So remember, forward privacy removes the linkage between a new file that is inserted and previous searches. Can we remove the linkage between a deleted file and later searches? Unfortunately, existing solutions are not efficient. And remember I said we have this client storage for these counters. So for each file and for each keyword, we need to store these values. In the paper, we say you can use Oblivious RAM to outsource this storage, but it adds a new round of communication. Can you reduce storage without adding new rounds of communication? Thank you for listening, and I will be happy to answer your questions.
Questions? Okay, I'll start. Oh, is there one over there? Great.
Would you get anything stronger if you sort of, instead of having just one counter, if you sort of preloaded the server with some random selection of keys in the future? So, sort of guessed what queries would happen, and you preload the server with some things for those, so that you don't actually have to send, so that after you do a query, just the deletion happens, and you don't always have to repopulate. You've sometimes already done it.
I see, something to maybe amortize some of the complexity, you mean, or? So let me, if I understood you correctly, first of all, in many searchable encryption schemes, because this started with static schemes, the description goes as follows. You have a build phase, a pre-computation, let's say, because you already have a set of files and that they contain keywords, so you build the index once and then upload it to the server. But for dynamic schemes, you may want to add a new file or remove a file during the process, so that's the problematic part. Now, in our case, this reinsertion of fresh keys and new random locations doesn't affect the asymptotic complexity. So it introduces a round of communication, but doesn't affect the overall asymptotic complexity.
Okay, I'll throw my question now. Can you go back to 44? Yeah, no, 42. Yeah,
Here?
great. But go to the last, no, that was the last frame of 44? No, go to the last, yeah, great. So when you do a deletion, it affects that right-hand table, but
yes,
not the left-hand table. So,
yes.
So the left-hand table is really overcounting the number of files for any keyword?
Exactly. So this, I don't know how visible is this. So here is the interesting part. So the optimal search cost would be OD, meaning D is the result set size. So you are only spending time and returning the files associated with that keyword. So now in terms of computation, the previous scheme, Sophos, has D plus number of additions and deletions. In our case, we have D plus number of deletions. So even though we deleted a file, the search should still go over up to the total number of files that were at some point associated with that keyword. So the server still spends that time. But for the deleted entries, the server will realize there's no valid entry there, so it's not included in the result.
But and is it the case that you get another benefit that when that search is complete, the server at least knows how many files actually match, and then when you do the when you recompute the new key for that keyword, do you only have to do the number of actual files that are left, or do you still have to?
Of course, so when you recompute, actually, you can do it because this number of deletions already leaked to the server. So we are not trying to hide it anymore.
Right. Any other questions? I have one more question, actually. So earlier on you said that forward privacy defends against file insertion attacks.
So forward privacy prevents the leakage between a newly inserted file and a previously searched keyword.
Right, but there's the attack where the server gives a file to be inserted, right? Like say the database is email and the server just sends email to the client, right? So the server knows that this file that was just inserted has these keywords, and so when one is looked up, it knows, this is that one of those keywords, right? So does your forward privacy technique stave off that attack?
So as far as I know, it doesn't fully eliminate.
Right, okay. Okay, any last questions? Standing between you and lunch? Okay, let's thank the speaker again. Speakers of the next session go to Claudia, and just remember, if you have not confirmed that you're going on the hike with the registration people, now is the time.